All right, welcome back again to Digital Srini, and this is part two of what we started in the last tutorial. And if you haven't watched that, I think you should. That provides a good baseline for you to understand what's going to happen right now. And although I will explain certain concepts we discussed in the last tutorial, when we get to the right functions here, that actually provides a good understanding of what our plan is, which is improve the diversity and fairness to our rankings, that we actually got from our recommender system, whether it is ALS or neural network. Yeah. So again, in the previous part, we talked about why accuracy alone is not enough, and we saw that the problem where all 10 recommendations were organic produce. We discussed the 4 dimensions of quality, the MMR algorithm, and the Gini coefficient for fairness. And now let's actually go ahead and implement it. Okay, and I am actually, as you can see, walking through the code, so please be patient in case I try to find where exactly the function is, a relevant function is. So I'm not going to walk you through every line here and bore you. Of course, you can ask ChatGPT and to summarize it for you, but I'm going to provide you nice context that connects the code to what we have discussed in the last tutorial. So let's jump in. I know I talk way too much. So the process is, did I put step 1, step 3 here? Not exactly, but the process, as I showed you as part of our presentation, I should have organized the code in terms of steps, like I mentioned in the last video. But step 1 is load or save data and the trained model from previous tutorials. In this case, we'll use the neural CF model that we trained earlier 2 tutorials ago. Generate 50 candidate recommendations per user, using our base model, which is the neural CF model. So these are purely optimized for relevance, of course. And measure the baseline diversity, like how many departments appear in the original top 10. And then we're going to apply MMR to re-rank those 50 candidates into a diverse top 10. And this is where obviously the magic happens, right? Measure improved diversity. Did it actually get more varied? Yeah, are we improving or not? Evaluate the NDCG trade-off. Like, of course, you want to keep the high NDCG scores, that you got from your original model, the baseline trained model. So how much relevance did we sacrifice by including diversity is what you need to quantify, right? And measure fairness also using Gini coefficient. Is exposure more balanced? And visualize everything, and of course show the example recommendations and so on. So our data set has, just to remind you, it's an Instacart data. We're taking a subset of it, about 80,000, in fact 78,777 users to be precise, and 1,500 products and 20 different departments. And then we already saved our train test matrices from tutorial 1, I believe, from tutorial 2. We actually saved the train and test splits so we can easily load them. And we trained the neural CF model from the tutorial about the neural CF. We load everything we need, and then we walk through the key functions in this tutorial. Okay, I'll show the results at the end after running the full pipeline, so we're not distracted. Yeah, so let's start looking at the code, and I want to show you the key aspects here. The first part is and this is calculate diversity. Let's actually get to the MMR algorithm and then actually go back and forth. So this is what I think is the best way to understand this. So I think right somewhere here, is it the next one? Diversity recommendations MMR. Yeah. So the heart of our system is basically this function, maximum marginal relevance. And let me show you how it works. And you see this formula. We discussed this formula in the last tutorial. MMR equal to lambda multiplied by relevance minus 1 minus lambda multiplied by max similarity. Okay, so by putting lambda equals to 0, you don't have any relevance, you have diversity. By setting lambda equal to 1, you don't have diversity, you only have relevance, and we need to find the balance between these two. So let's see, normalized scores right here. And first we normalize the relevance scores to between 0 to 1. Okay, that's what we are doing right here. Remember the scores that we get from the dot product of user multiplied by item. So embeddings, I should say. This puts relevance and similarity both on the same scale. So lambda weighting makes sense. Otherwise, the lambda weighting I showed you earlier obviously does not make sense. Okay, and then scrolling down best IDX and then selected items. So we select the first item, always the most relevant item. Yeah. That's the first item. And now the question is, what do you pick next and the next and next? Okay, so no diversity penalty yet when you pick the first item. We trust the base model's top choice. That's what this part is. And then for each of these items right there, okay, in this loop right there, remaining indices. Yeah, so in this part, this is obviously the iterative selection for each remaining slot, second and third and fourth and fifth. First, we already picked, yeah? We evaluate every candidate, okay? So this is what this part basically is. And if I have to, let me explain this in simple English. Let's say we selected top one as, I'm hungry now. Let's say we selected top one as trail mix. From the snacks department. I hope outside of the US it makes sense. This is like chips and other stuff combined. Okay, so let's say that is our trail mix is basically a snack, a junk food. That's what we selected. That's our first item. The second, because I'm getting ready for a football game or something. Yeah, so trail mix is our first thing. What should be the next item, the second item? So let's say candidate A is organic tortilla chips. These are the Mexican snacks, organic tortilla chips. Of course, also snacks. I mean, I just watched a football game last night and I'm just thinking of what I have, what I did. So again, so organic tortilla chips. And obviously the relevance is very high, right? Let's say relevance is 0.85. And similarity to trail mix equal to 0.7. Okay, so relevance is coming from the from our ALS or neural network model, and let's say 0.85, and similarity to trail mix. Of course, it's the same department, so very high, 0.7 similarity, and your MMR score is nothing but, let's say your lambda is 0.8, right? Multiplied by 0.85, relevance is 0.85, okay, minus 0.2 because we set our lambda to 0.8 minus 0.2 times the similarity is 0.7. Okay, so you'll get something like around 0.5-ish, 0.55, 0.54 or something of that sort. Okay, now think of another item that's not a snack. Let's think of a Greek yogurt, something healthy. That's dairy. And let's say the relevance is 0.75 because, again, our algorithm or relevance algorithm, ALS or neural network gave us 0.75. And similarity to trail mix is completely 0. It's a different department. It doesn't have much of a similarity. And if you calculate this MMR again, so your lambda is 0.8. We set it to 0.8 times the relevance is 0.75 minus 0.2 times the similarity is 0. The second term is 0. So you get 0.8 times 0.75, about 0.6 right here. So Greek yogurt in this case wins. Even though it's less relevant, it adds diversity because if you get the same snack as organic tortilla chips, 0.5. I did buy both of them, by the way, if you wonder, over the weekend for yesterday's football game. So Now let's look at the similarity, right? I mean, we went through that function earlier. I'm jumping back and forth to make sure you understand the key aspects in the right order. The similarity function, calculate item similar. Oh, I called this fast because I was doing this one by one and it was super slow, and I kind of changed this, and you'll see from the structure here. But what this is doing here is department 1 IL1 and department 2. If department 1 equals to department 2, all that is 3 levels. 1.0 for same IL. Where is it? Return 1.0 if it's from the same IL, 0.7 if it is from the same department, 0 for if it is different departments. That's what we are basically setting here for item similarity. Yeah. Okay, and let's see, around, where is that? Let me scroll back. I just want to show you one other where we actually pre-compute all departments and IL mapping. So we just have to do this once. There should be similarity cache. Oh God, I'm just staring at it right there. Build similarity cache right here. So this is where it's actually, it's one of the key optimization steps I kind of had to figure out and added later on. This makes similarity lookup almost instantaneous. Without this, we have to query data frames millions and millions of times. Like we have a data frame, you have to query that millions of times. And with caching here, it's just basically a hash table lookup, like more than 100 times faster. Okay, so that's MMR. Pick the best item to start with, then iteratively add items that balance relevance with, of course, being different from what we already have. That's basically what MMR is. Okay, and now let's actually go down to measuring the diversity score. And I think I put all measuring stuff right in the beginning. Calculate diversity. I think there is oh God, calculate diversity. I just looked at calculate diversity. I thought I called it measure diversity. This is calculate category diversity. This is basically measuring if MMR actually worked, right? Did we get more variety or not? That's what this function is. And you can read the docstring over there. What it does is for each user, it extracts the department for each recommended product, count the unique departments that we have in the recommended, average across all users. So it's pretty simple. Yeah, if a user gets, let's say, 7 different departments out of 20 possible, their diversity score is 7 divided by 20, which is 0.35. Okay, so the key metric is average departments per user. Okay, and our results actually showed that before MMR, 2.3 departments per user, and after MMR, 3.7 department per user. Yeah, so that's a very nice improvement. And this is exactly how we quantify the recommendations. Basically getting more varied. Tough to say for me for some reason. Okay, I think that's and measuring fairness. It's did I put that after diversity? Oh God, measuring fairness. I went all the way down. So measuring fairness, let's actually see somewhere around here. I think I called it measure item exposure. What is this? Calculate Gini. Yep, right there. Calculate Gini coefficient is right here. Measure item exposure. The fairness part here. It's about long tail exposure, right? So these are the items that don't see the daylight often. So are we giving niche products a chance? So first we count how often each item actually gets recommended. Okay, this is just simple counting. If we recommend, if we actually recommended an item to all 79,000 users with 10 items each, that's 787,700 something, right? Total slots we have distributed across our 1,500 products. I hope this makes sense. So what we'll see later is before our MMR, 1,055 items with 0 exposure, and after MMR, 1,020 items with 0. We kind of have some slight improvement, but counting 0 isn't enough. We need to measure inequality also. Yeah. So that basically, so how many items are never seeing anything, like 0 is one thing, and the Gini coefficient actually tells you about the imbalance. I hope that makes sense. Okay. Excuse me. So this is the Gini coefficient part, and again, this is the equation. If you want to dig deep, I think you should, if you are into machine learning. And Gini typically, not typically, Gini ranges between 0 to 1. Perfect inequality is 0. And usually between 0 to 0.3 is very fair. 0.3 to 0.5 is acceptable inequality. 0.5 to 0.7 is concerning. It's not, and 0.7 plus is severe inequality. Okay. And our results kind of show something interesting. Before MMR, 0.896. After MMR, 0.896. I think that's what we got initially, but we'll see again later on, right? The fairness did not improve much. You will find scenarios where fairness did not improve much, because with lambda equal to 0.8, we heavily prioritize relevance. So then I adjusted. I'm talking about initial, I'm telling a story about how I initially got nothing, and then I had to adjust the lambda. And if we use lambda 0.5, which is more balanced, we'd see bigger fairness gains and so on. Okay. Again, it comes down to playing with these parameters at the end. You may not see much improvement, so you adjust different parameters. Remember the triangle, trying to find that sweet spot in the triangle from the last tutorial. Okay, the complete pipeline, somewhere around here, I think. Load, process data, plot diversity comparison. This is just plotting, plot exposure distribution, and plot Lorenz curve is the curve I showed you in the last tutorial, just for visualization purposes. And where is it? These are all plots. We'll look at the plots later on. And get department per recommendation, so sample comparison, and main load process data. I think I missed this load process data function. So, but obviously it's somewhere. I don't want to waste your time trying to find that. So we load everything, obviously, with the load process data. We load everything we saved in the previous tutorials. Then we generate the base recommendations. We are loading the trained model right there. Oh, I did put step 1, step through. It's just that I thought it was earlier. Okay, so we are loading the trained model, and then we generate the base recommendations, and right here. And the base model generates, again, remember, in our case, it generates 50 candidates per user, and they're purely optimized for relevance. And we need 50 because MMR needs choices for diversity. Yeah, you can't just do top 10. So you need 50, possibly even 100. And then once you get those, you're going to apply, here we are measuring the original diversity, but then we are applying the MMR diversity right here to improve the diversity. Again, this is where we re-rank using MMR. Again, pretty quick. This takes like 70 seconds or something. The whole thing is pretty fast. That's what that's why I'll show you the results. And of course, once you do that, you have to evaluate the trade-off. So you measure improved diversity and evaluate the NDCG trade-off, like what is the new score for NDCG. If it is a big difference and you're sacrificing a lot of relevance, that's not good. You need to find the right balance again. Okay, and of course the last part is just of course Gini index, like we are going to measure the fairness, and then we are generating all these visualizations. So let me run this, and I'll pause because it's going to take a few seconds, and then I'll actually continue by discussing the results. So just give me a few seconds. Okay, so this is done, took like about a minute or so. Let me show you what we actually achieved after running this full pipeline. So let's go all the way. And there's a lot of you can go through all of these. I mean, the code is down under description, so you can actually run these yourself. So I'm not going to waste your time going through every one of these. It's interesting actually to see what the original is and what the diversity wants, pure relevance all produce, a couple of beverages, produce, and then you have a bit more dairy, bakery, deli, frozen. So you can see the diversity right there. The top items before and after MMR. But I think the more important ones here is let's actually start by looking at which one, the NDCG trade-off. Okay, so did we actually compromise a lot on our NDCG? Of course, original was 0.0807, and now after diversification, again, I changed my lambda. Originally was 0.8 and I saw nothing here, but at the same time the diversity did not improve at all, so I adjusted my lambda to 0.5. Now I'm seeing 0.0789, not much, 2% loss in NDCG for diversity gain. Now how much did diversity actually gain? Let's go ahead and open this, and there are two plots. The left side is basically the distribution, and the right hand side you can see the original 2.3 and the current one. But that's basically 2.3 departments per user. That's what the 2.3 means, and 3.7 is 3.7 departments per user. Okay. So I'm thinking whether I should say anything about the left hand side. You can see these orange ones, the original ones. Most users had 2 to 3 unique departments, peaking at about 2. The diversified blue has much better spread right here. Most users now have 3 to 4 unique departments, and the distribution itself is shifted to the right. That's the key point right there. Okay, and fairness analysis, let's see, exposure, do we have exposure distribution? Yeah, we have the exposure distribution right here. Let me expand this so you can have a quick look at it. The histogram shift, in this case, I'm thinking which one to make sense. So again, 4 subplots, as you can see. These are exposure histograms on the log scale. So the original is the one on the left hand side. So there is a steep drop off right here. Most items get very few recommendations, and the diversified slightly flatter distribution. That's why I was like thinking whether I should even talk about this. And bottom shows the Lorenz curves, and severe inequality, the curve below. So it's still, we haven't improved the fairness quite a bit, I should say, with the parameters. I should apologize. I changed the parameters to it, for this tutorial to see which one actually works fine and all. The most, I would say, a cooler thing to do is almost like hyperparameter tuning. Change these parameters to actually find the center of that triangle, like Gini, fairness, and your NDCG score, and find that equilibrium between all of those. That would be ideal, like to do that in an automated way, but just by manually changing things, obviously you're not seeing much of any improvement by looking at this one. In terms of fairness, we did make improvement in terms of diversification, but not in terms of fairness. Okay, so I think that's where I should end. Basically, MMR re-ranking is one of the key things we have done. Iteratively selects items that maximize lambda multiplied by relevance minus 1 minus lambda times max similarity, right? So we have done this similarity caching for speed purposes, so we don't have to do this millions and millions of times. And the diversity measurement, again, key takeaways, the diversity measurement, it counts unique departments per user, and we went in the average from 2.3 to 3.7 departments. That is 65% improvement, if you can see. And the fairness measurements, it calculates the Gini coefficient. We calculate Gini coefficient for exposure inequality. Unfortunately, it stayed at 0.89 or whatever we have, and we haven't improved that quite a bit. I think I can talk forever about these, but I hope you understand the importance of adding diversity and fairness. Of course, it's tough to achieve fairness. As you can see, we haven't achieved it, so we need to play with this a bit more. And that's it. For a true production system, these are the ones that you have to look for. Look for in your production model. Again, I keep talking, but because this is the last video as part of this series, and let me know if you want something else more on this specific topic. If so, please leave them in your comments. Otherwise, just hit the like buttons and subscribe buttons and spread the word, man. I mean, I hope more people find, maybe mine is one of those tales on YouTube platform. Some of you found it and you're watching it, but for others to know, I can use some help from you in terms of word of mouth. Thank you again. And in the next series, I'm hoping that would be financial analysis, but let me know if you want a specific application area where you want me to see certain videos from me. Thanks again, and let's meet again in the next tutorial.